All right, students, thanks for bearing with me on this. We are going to try an experiment here. We're going to do an online PowerPoint presentation and see how that goes. So tonight we're going to be going over the ANOVA and F tests. The ANOVA is the F test. The ANOVA test, or the F test, is similar to the T test. If you remember last week, we went over comparing two groups to see if there was a significant difference between the two sample means. But what if we have a situation where we have multiple groups? In that case, for example, we might want to compare the scores of students at public, private, and home schools and see if those groups are significantly different. Or we might want to say public, private, charter, and homeschool and see if there is a significant difference anywhere between any of them before we go on to look at is there a difference between public and all the others. So if we have multiple groups like that, then we would want to use the ANOVA test or the F test. Before we go on, let's talk about why we couldn't just use the T test. If we wanted to use the T test, we would have to use the T test multiple times. So in the public, private, and homeschool example, we have to compare public to private to homeschool, and then private to homeschool. So there would be 3 tests, and that means that number one, it would be tedious, and so we wouldn't want to do that, number one. And then number 2, we wouldn't want to do that because by doing multiple tests, that increases the likelihood that there's going to be a test that's significant just by chance alone. And that problem is known as what is known as family-wise error rate. So it is appropriate in these situations to run an analysis of variance and see if you have any sort of difference first, and then we'll talk about how to test the differences between the different groups among the multiple groups that you have. So when we go from T to F, we need a way to test whether there is any significant difference anywhere in that array of categories. If this statistic tells us there's no difference, then really there's no point in further analyzing the data. And that test that we'll run tonight is the ANOVA. So let's do a little SPSS exercise to get us to thinking about the data first. Let's think about whether there is a difference in the mean of the age of different races of people. How can we graphically do this, or how can we get a visual understanding of it? We can do that by doing a box plot. So why don't you put this on pause, this video on pause, and run a box plot in GSS, and then come back to it, and I'll show you how I ran the box plot and what I see in the data. So to run the box plot, we first go to graphs, chart builder. Okay, don't show that again. Okay. And we want to select which graph we want. So we want a box plot. And then we want age of the respondent on the x-axis and on the y-axis, and then race of the respondent on the x-axis. The only reason that I do this example is just because I need some sort of continuous variable as the outcome, and we need some sort of categorical variable as the different categories. And so if you remember right, if you remember about this data, I think we've looked at this before, there are three categories of people. There are white, black, and other. That's how it's coded in the data set. So it looks like there is a difference in the means. White is slightly higher than black, which is slightly higher than other, but there is significant variation, particularly with the white and the black, and even the other has, some serious outliers that, would seem to suggest that maybe there's a difference, maybe there's not. You can't really tell, so you're just kind of just sitting here looking at the data, and so now we know that the mean value for white is slightly higher than black and slightly higher than other. The question is there any difference anywhere? Is there a significant difference anywhere in the data? So let's talk about the f-test, and then we can run the statistical test to see if there is any difference anywhere. So what is ANOVA? It stands for Analysis of Variance, and it's basically an estimate of the variability between the groups, and then relative to the variability within each group. So formally or defined, between group variation is the variation among the means of the different categories or treatment conditions, both because of chance and because of different treatment effects, if any were to exist. The within group variation is the variation that would be due to chance among the individuals in each one of those groups. So basically what we want to see is there more variation between the groups relative to within the groups. That will tell us if there is a significant difference between any of the categories. The f-test itself, f is the same exact thing as the ANOVA, is just between group variability divided by the within group variability. So graphically, what this refers to is that in this example, there is a very large difference between categories 1, 2, and 3 and categories 4, 5, and 6. And so we can see that these categories likely come from two different populations, or there's something that makes category 1, 2, and 3 more alike, and category 4, 5, and 6 more alike. So in this case, we are likely to see a significant f-test. So, and that's because you can see a large difference in the means, at least between the first three relative to the last three. And the variability, those distributions around each of the 6 categories, is also relatively small. So we see that it is likely that 1, 2, and 3 come from a population that's different than 4, 5, and 6. So if we were formally doing a hypothesis test, it's likely that we would reject the hypothesis in this case, and that would say that at least one group is significantly different from the others. Because the F-test is both the between group variability and the within group variability, the amount of variation just within the groups matters significantly to the overall F-test. So here, groups 1, 2, and 3 are the same distance away from groups 4, 5, and 6. But as you can see, their distributions significantly overlap the distributions of all the others. So there's the same amount of variation between the groups, but the within group variability is significantly greater, and so we would be much less confident in this case that the samples would be drawn from different populations. So again, to just reiterate what we talked about in the first graphical example, the variability between the groups was large, and the variability within the groups was relatively small. So in that case, the F would be large, and large F's typically mean that it's more likely to be significant. Now, the F, when we get into the actual formula for it, like the t-test, it's based on degrees of freedom, and so it depends on the number of groups, and it depends on the number of observations in each group. I'm not going to say F is significant at this point, or F is any particular number. I'm just saying that we can see graphically that it's likely that if we had this scenario, the F is large because there is a significant, or there appears to be an observable difference between groups 1, 2, and 3 and groups 4, 5, and 6. And so here again, the arrows in the middle group is the variability between the groups, and those arrows that just appeared are the variability within the groups. Again, to belabor the point about variability between groups and the variability within groups, here is the variability between the groups. Again, it is the same amount of variability between the groups, but there is much wider variability within the groups. And so in this case, the F would be much smaller because the denominator is larger relative to the numerator. So it's less likely that we would be able to reject the null hypothesis that there is no difference. Okay, so the formal F-test is the mean squares between divided by the mean squares within. Mean squares between is defined as the sum of squares between divided by the degrees of freedom between, and the sum of squares between is just the sum of the number of groups times the group mean minus the grand mean squared. And then the degrees of freedom is just the number of groups minus 1. This is also known as the numerator degrees of freedom. The bottom, the denominator in the F-test, or the F-ratio, is the mean squares within. The mean squares within is equal to the sum of squares within divided by the degrees of freedom within. Again, think of this as testing the variability within each group. So the sum of squares within is just the sum of each individual x minus the group mean and then square each one of those. So, and then the degrees of freedom is just the number that are in each group minus 1, and all add them up. Or if you would do the math on this, it's just the total number of subjects or the total number of observations minus the total number of groups. And that is the denominator, degrees of freedom. So to do a little example here, we have annual sick days at 3 different sites. So think of this as the city of Charlotte and 3 different departments. And you want to see, maybe the 3 different departments are 2 different types of sick leave policies that have been randomly assigned to the departments, and the number of 6 days it would be maybe the number of sick days in a month for each one of those. So in Site A, we have 5.3 sick days, 6 sick days, and 6.7 sick days. In Site B, we have 5.5 sick days, 6.2 sick days, 6.4 sick days, 5.7 sick days, and in Site C, we have 7.5 sick days, 7.2 sick days, and 7.9 sick days. So stop and ask yourself, if I were eyeballing this, would I think that there is a significant difference between any of these sites? Well, let's look at the averages for each one of them first. In Site A, we have 3 observations, and the average number of sick days is 6. In Site B, we have 4 observations, and the number of sick days is 5.95. And in Site C, we have 7.53 sick days. So on the surface, it appears like Group A and Group B might be similar, right around 6 sick days, and Site C might be different at 7.5 sick days. But we have to ask ourselves, is that approximately 1.5 days different? Is that significant enough that we're going to determine that there is a difference between the sites? So how do we do that? We'll calculate it by hand here, but let's first go through our steps that we are always going to do when we do a hypothesis test. First, state the research hypothesis. The research hypothesis being here, does sick leave usage differ based on the work location? The statistical hypothesis then would be that the null hypothesis would be that the average number of sick days among the 3 sites is equal. The alternative, what we're trying to reject, is that there is a difference between somewhere between mu1, mu2, or mu3. So actually, I don't like how I stated that. H0 is false is probably not how I would want you to state that. Normally, I would probably want you to state something like mu1 does not equal mu2, or mu2 does not equal mu3, or mu1 does not equal mu3. Now that I see my slides, I see now why some students have used this sort of notation, and maybe not a good notation. So in this test, we are actually saying that there are no difference between any of the means. And so we really can't posit a directional hypothesis in this case. In the ANOVA case, we're just saying that there is something that is different. Yeah, so here is how I would actually like you to state the null and alternative hypothesis for ANOVA tests. The null here being that all of the means are the same, and then the alternative being that mu2 does not equal mu3, or mu1 does not equal mu2, or mu3 does not equal mu1. That would be the possible combinations. That is more technically correct. Then we'll set the decision rule, alpha equals 0.05, and then we'll look up the value on the F distribution chart, keeping in mind that the degrees of freedom between is 2 and the degrees of freedom within is 7. We can see that the degrees of freedom between is 2 because degrees of freedom between was just the number of groups minus 1, and then the degrees of freedom within is the number of subjects or the number of observations minus the number of groups. So there were 10 observations minus the 3 groups is 7. So the F critical value with numerator degrees of freedom of 2 and a denominator degrees of freedom of 7 is 4.47 at 0.05. This test also has in the dark p less than 0.01, which corresponds with the area outside of the curve, which is equivalent to what we would consider our alpha level. So alpha less than 0.05 is 4.47. So computing the ANOVA F statistic, this is how it would go if we were just going to use algebra all the time. We have the data arranged in spreadsheet type format. We have the individual observations on the far left column. Next we have the groups, site A, B, and C. And then we have the group mean. The group mean for group A was 6, the group mean for B was 5.95, and the group mean for site C was 7.53. So if we take and calculate the within variation, we'll first subtract the next column to the right of the group mean. We'll subtract the individual observation minus the group mean. So 5.3 minus 6 is negative 0.7. Then we would do the same thing for each one of the next observations. So 6 minus 6 is 0, 6.7 minus 6 is 0.7, 5.5 minus 5.95 is negative 0.45, and so on and so forth. Now, we couldn't just stop at subtracting the individual x minus the x bar, because then those differences would cancel each other out, right? Because that's what happens with an average. So we have to square it. The next column in the within, x minus x bar quantity squared, shows that negative 0.7 squared is 0.49, 0 squared is 0.00, 0.7 squared is 0.49, negative 0.45 squared is 0.2, and so on and so forth. So then we sum all of those up, 1.76. We then take the 1.76 and divide that by 7. So the total there is the sum of squares. to get the mean squares, then you take 1.76 divided by 7, and so the mean squares within is 0.25. Doing the between is very similar, although I would point out that the grand mean for all of the observations, if you would calculate the mean for all those observations in the left column, is actually calculated for you down in the very bottom left corner, and that is 6.44. So if we take x bar and calculate the between variation, so x bar minus x bar bar, or the group mean minus the grand mean, that means 6 minus 6.44 is negative 0.44. And then we would do that for all of the different groups. So group A is negative 0.44, group B is negative 0.49, and group C is positive 1.09. So you square that, and you get the sum of squares between for each one of those groups. You add all of those up, and that is 5.13. And then we take 5.13 divided by the degrees of freedom, or 2, and that gives you your mean squares between of 2.56. So the F-test is just 2.56 divided by 0.25, or the mean squares between divided by the mean squares within. So that is an F value of 10.22. So we now know that the F value is 10.22, and our alpha critical value in the F table was 4 something. So is it significant? The answer is, of course, yes. We are going to reject the H naught. There is a significant difference. 10.22 is much greater than 4.74 on the F table. So 10.22 would be much more unlikely than even our alpha of 0.05 level. So how would we interpret our results substantively? There is a significant, or not substantively, statistically, how would we interpret our results? There is a significant difference in sick leave usage between the work sites. That's all we can say at this point, is that the F-test tells us that there is some difference between the sites. So to do that, we would need to do what is called a post hoc test to make pairwise comparisons after we have a significant F-test. If the F isn't significant, then there's really no reason to do a post hoc test, because we know that there shouldn't be any significant difference anywhere between the variables. You can do the ANOVA in Excel. You could put all of those numbers in a column, and the different groups, and it will spit out the same exact thing that we showed here. The F critical value is 4.74, the F value is 10.22, and the P value is actually 0.01. So significantly reject the null hypothesis. So let's talk about the assumptions of ANOVA. First, we have to, or we are assuming here that being in category 1 doesn't affect being in category 2 or 3. The samples are independent, so we wouldn't think that the variability between the groups is going to be influenced by how we take the samples. Second, the dependent variable would be interval or ratio level, what we have been calling continuous variables. It's not appropriate in this situation to use a 0-1 dependent variable. That would be more of a chi-squared type test, which we'll talk about next week. So when we're running ANOVA, we have more than two groups that we're testing, and the outcome is some sort of continuous variable. Each group would have to be approximately normally distributed. You can check this by looking at box and whisker plots, or use some assumptions here. The ANOVA can handle some normality, but not severe outliers. So if there were one outlier that was really huge, it might significantly pull the group mean out and make it different from the other groups, even though maybe those other groups wouldn't necessarily be significantly different if that outlier were excluded. So you should run a box and whisker plot and check for really severe outliers. And finally, the last assumption of the ANOVA is that the standard deviations of each group are approximately normally equal. And so our rule of thumb here is that the ratio of largest to smallest sample standard deviations must be less than 2-to-1, or approximately 2-to-1. So if we go back and we look at our example here, we can see that there doesn't appear to be any serious outliers, and then the variance to get that into standard deviation, you'd square root that. And so the variance or the standard deviations, if you square root those are approximately 2-to-1. So we're very close to meeting the assumptions of the ANOVA. It's easier when we're doing this in SPSS to check these assumptions, because you can just run summary tables and check these things as you're going along. Again, here is the F table with the numerator degrees of freedom on the top, and down the left side the denominator degrees of freedom. I had that earlier. Analysis of sick days from ANOVA is in SPSS shows the same F test 10.216 and the significance of a little bit more precise. In Excel, it only rounded to two decimal places. Here it's rounding to 3, so significance is 0.008 when we're a little more precise with SPSS. I also show something that kind of is going to tip my hand to the fact that regression can also do the same sort of thing, and it has the F test in it. So if we regress those 3 categories on the outcome, we get the regression output. and the F test is shown, 10.216, significance 0.008. So that gives us more confidence, even more that the tests are working as they should. Okay, last thing we're going to go over tonight before you can stop watching this video. We're going to test the individual differences between the categories. And to do this, we'll use the Tukey's test. The general ANOVA answers the question, is there any difference between the categories that's significant? So it can be, when you get a significant value, it might be category 1, it might be category 2, or it might be category 3. You don't necessarily know. To answer which of the differences are significant, you will use these post hoc tests, and the common test that we tell students to run is the Tukey's test, and that just compares the differences of means of each category relative to each other. And this is an option that you can tell SPSS to do when you're running the test in SPSS. So it doesn't take any more additional calculation or anything. It's just an option that you run to do the post hoc test. Okay, so let's think about something that might matter to public policy or public administration in our data set that we could answer. Particularly those of you that are going to get your master's degree and have put off having children, or may have put off having children, you might want to know if your life circumstance is any different than anybody else's. So we could potentially answer that question here, because we have different categories of schooling for each of the individual respondents. So a categorical variable, and then the age at which their first child was born. And so to do that, we can compare the means using one-way ANOVA. That's the test in SPSS. And then the dependent variable is this age KDBRN, or age kid born. And then the factor is the categorical variable that we care about, and that is the degree. And then click on post hoc. This is under options, equal variances assumed, and Tukey, and then click continue, and then click OK. I'm going to wait a second. You can pause this video while you run SPSS, then I'll show you how I did it to make sure that we agree. Okay, so when we do this test, we're going to go to compare means. So we're still comparing means. We're going to click on one-way ANOVA. Then we're going to click on display variable names and sort alphabetically. Age KD born. That is our dependent variable. So that's the age when they had their first kid. And then the factor is the highest degree that they have. So it's going to look at whether people that don't have any degrees or have kids at a different age relative to people that have high school degrees, have junior college degrees, have bachelor's degrees, and so on and so forth. And the variable here that we want to put in factor is degree. Put that in there like that. Then we click on post hoc, and we're going to click on Tukey and click continue, and then click OK. Okay, so first off, let's look at the ANOVA. The ANOVA is very large. You can see here that the F test is an 88.558, numerator degrees of freedom of 4, within group or denominator degrees of freedom of 1,484, and so that means that there's a significance of 0.000. It is very, very, very significant. So apparently the people that have different degrees come from significantly different populations when it comes to their decision of when to have children. So the question then becomes, where are there significant differences? And so you can see here the different categories, and it compares the less than high school relative to all the other categories. So less than high school relative to high school, so I minus J. So it's saying here that they have children 1.6 years earlier than high school. They have children 2.6 years earlier than junior college, 6.2 years earlier than bachelor's degree, and 7.7 years earlier than people with graduate degrees. And they're significant. The less than high schoolers are very, very, very significant. The high school people with high school degrees are significantly different, of course, relative to less than high school. We've already determined that. They have kids 1.6 years later than the less than high school. And they have children 0.95 years earlier than junior college. So that is not significant. You can see that that is not less than 0.05, so we can't conclude that high school and junior college that there is a significant difference there. There is a significant difference, however, between high school and bachelor's degrees and high school and graduate degrees. Junior college is the exact same as the high school, significantly different than less than high school, not significantly different relative to high school, and significantly different relative to bachelor and graduate. Finally, the only thing that we haven't looked at is the relationship of bachelors to people with graduate degrees. And what we see here is that people with bachelor's degrees, on average, have children 0.894 years earlier than people with graduate degrees. So slightly earlier, but again, not significant. So we wouldn't conclude that there is a significant difference between bachelors and people with bachelor's degrees and graduate degrees in terms of when they have their first child. So in conclusion, there's a lot of difference here between based on degree, and that makes a lot of sense. The decision of when to have kids is intimately related to people's decision of how long they can put it off to go and invest in their higher education. So what we see here is that there is a significant difference between almost all the categories. The only categories that are not significantly different, really, are the difference between high school and junior college and the difference between people that get bachelor's degrees and graduate degrees. So quite interesting, probably what we would expect if we really sat down and thought about it. One more SPSS example for you to do. Let's revisit the age and the race, just because we set it up with the box plot. Run the ANOVA test to determine if there is any difference between the age of the respondents based on the race. What does this tell you? Well, I'm gonna pause here again for just a moment. You pause the video and run the SPSS. And when we return, I'll walk you through how to do this and how to interpret this. All right, so compare means, one-way ANOVA. Let's get rid of the variables that we had earlier about the age at which kids have, age at which kids are born, and then so we want to put in there the race would be the factor, the category, and the age would be the dependent variable, so a continuous variable. Input error when reading a case. Well, that's not good. I wonder why that happens. Is it because well, I don't know what to tell you, folks. The SPSS doesn't seem to be working, so I'm going to close out of it and restart it. Reload the data set. Hopefully I can edit this out of my video. Okay, opening that sweet data set again. Compare means, one-way ANOVA, the age of the respondent, and then the race of the respondent. Click on that. Click on post hoc. Key, continue. Okay. Alright, there it goes. For some reason it just was having problems with me for a minute. Okay, so we can see here that the F is significant. That difference, those differences were significantly different at alpha less than 0.05. So we reject the null hypothesis that all the means of the groups are the same. There is some significant differences here. So when we go back down and look at the post hoc test, we can see that when it comes to significance, the difference between white and black is significant at less than 0.05, and the difference between white and other is less than 0.05. The difference between black and white, as we just talked about, is significant at 0.05, but the difference between black and other is not significant at less than 0.05. It's very close, It's very close, and sometimes we'll even note that it's very close, but we would not reject the hypothesis that there is a significant difference between black and other. So, why might this be the case? Maybe different races have different access to medical care or something like that, and so it's when we look at these numbers in data, sometimes it's really shocking to see that in fact there are differences between people just based on their race. There might also be other reasons for this, but we can at least say that there are significant differences, at least between white people and black people and white and other people based on our data, and based at a 0.05 level of significance. Okay. One final thing. Go back and do the sick days in SPSS. I'm going to let you do this on your own. Add the sick days into a blank SPSS spreadsheet. Run the test, and then do the results conform with the results of Excel. And with the Tukey's test, what does this tell us? So I'm not going to do this for you. You can go and do this on your own, but if you, I'll get you started here. If you want to have a new data set, you click New and Data, and then type in your sick days. 5.7, 6.0, etc., etc., etc. Change the name here. Sick days. Oops. And then let's go back to our data view here, and then put in group 1, and so on and so forth. You will need to go and change your variable type from numeric, or not type, measure. We want to change the measure to nominal for the groups, and we want to change the measure to scale for the sick days. And that basically is telling SPSS that your sick days are continuous variables, and that the numbers that represent the different groups, you need to treat them as groups and not as numbers. So that's how you would do that. So do that for all the sick days, all the groups, and run the test. That should give you an F that's the same as what I have from Excel, and then do the Tukey's and see which is that site C, is it significantly different? Spoiler alert, it is. Okay, so next week do chapter 6, problems 1, 2, and 3, and I think you've already done all the reading that you need to do. Just review the reading for this last chapter on the chi-squared, because next week we're going to go over chi-squared. So, Thank you for bearing with me with this video and all of that, and the technical problems that we had creating it. So I look forward to getting your comments and feedback. We'll go over and answer questions next week before we move on to chi-square. All right, I look forward to seeing you shortly. Bye.